although that's a fairly creative problem. And the problem says due on Thursday. Yeah. So where were we? We looked at vibration and rotation for, that's okay, heteronuclear diatomics. We defined vibrational temperature. And we saw that that's the vibrational partition function. And we saw that at very high temp, the vibrational partition function simplifies to this expression, but the caveat is that this temperature has to be much higher than room temperature for most molecules. So this approximation is not going to be of much use under normal conditions. Similarly, we just defined a rotational temperature as I being the moment of inertia, and sum over all the states, that energy levels rather, that's the degeneracy. I guess we can do it in terms of KT. That's all. So that the high temperature limit so in the high temperature limit, the vibrational and rotational partition functions look very similar in terms of these constants, the vibrational and rotational temperature. For most molecules at sort of room temperature, this condition does pertain, so this is a good approximation, and you can always improve upon it. Two caveats. This is based on the harmonic oscillator approximation, and all of this is based upon the rigid rotor approximation. And you can, actually this is based on both the harmonic oscillator and ridge rotor. So you can improve upon those if you want. We, after developing the partition functions, developed expressions for the energy and for the heat capacity by way of example. And I want to return to the heat capacity in order to make a point I kind of wish I made a little stronger last time. So let's see, I'll think just about vibration. That's all that really, I just wanted to emphasize. So classically, CV for vibration is R, the gas constant, or in K for some number of molecules in. We saw from our expression, quantum mechanically, I just want to see if I'm missing a 2, I'm not sure. Yeah, that's correct. So obviously these expressions are a little different, and when we do a picture of CV vibe, using the quantum mechanical expression we developed, we saw this. So 2 points. One is that, as we discussed last time, heat capacities, the discrepancy between the low temperature behavior of heat capacities and the classical prediction was one of the driving forces for the development of quantum mechanics. And so, of course, this comes right out of our formalism. This qualitatively, the quantum mechanical expression qualitatively gives what you see. And the other thing I alluded to, and I want to say again, is Einstein developed, what in the early days of quantum mechanics, in this vein, Einstein developed a formula for the heat capacity of a crystal that matched the low temperature behavior measured pretty well. So it's a famous equation. And I want to write down, again, what it looks like. So this is Einstein, and it's for a crystal. We'll probably get to this later in the course. I'm kind of jumping the gun, but I want to compare. Let's just. So if you examine these two expressions, I'm missing something. Obviously they look very similar. The exponential behavior is the same, and even this factor right here is very similar. NK here, NK here. The only difference, qualitative difference, is factor 3. Well, if you look at Einstein's mental image of a picture, or the model he built this on, it's very simple. Here's a sort of crystal lattice. in 2D. Of course, it's really 3D. And Einstein's approach to develop this equation was very simple. He said, let's assume that what's going on in this crystal is that each of these, we'll think of a monatomic substance right now, a monatomic crystal, can vibrate freely in any of three directions, harmonically, in the x direction, the y direction, or the z direction. So his equation for the heat capacity was based on this harmonic oscillator approximation, just like ours was. The only difference, or the basic difference, is that we have a one-dimensional harmonic oscillator, just this diatomic molecule like this. And he has, in the crystal, there are 3 degrees of freedom, each of which harmonic behavior occurs, and that's the source of the 3. So not surprisingly, same thing. And then I think sort of the last point I want to make in this vein is how trivial this all seemed, right? I mean, we set up our energy levels. We knew the results from quantum mechanics for the energies of our harmonic oscillator and the energies of a rigid rotor. And it took us no time at all to develop an expression for the vibrational partition function. It was just some trivial mathematical manipulation, summations. And similarly for rotation, it was trivial. In this case, we integrated and improved if we wanted to be clever. It was really quite trivial. And from those partition functions with a derivative, you get the energy, and with another derivative, you get the heat capacity of all things. Trivial. And so what I want to bring home is how convenient the formalism is. The reason it was trivial is that we developed an elegant formalism. In terms of the partition functions, it gives you all these thermodynamic functions. So the triviality of this demonstrates the utility of our approach. Questions, comments? Before I go on to the, one other thing before I go on to the homonuclear case, and that is a homonuclear diatomic case, and that has to do with some conventions that you probably read about, but I didn't emphasize. Just want to say something about conventions. And it's simply the convention on what we choose as our zero of energy. So if I think of a homonuclear diatomic, some distance r, let this be the energy vertically, just of my single molecule, and this is r. We know that qualitatively that's what the energy is going to look like as a function of r. This asymptotically will go to some value, and this corresponds to separated atoms. So this is the separated atom. Energy. This difference here is the well depth, and it's usually given the symbol D with the superscript E. Now, there's going to be a 0-point vibrational energy. That's the lowest vibrational energy allowed. And we know that, so let's just put these here. That's 1/2 h nu. That's the 0-point energy. And this difference here is D0. And spectroscopically, what's measured is D0, because when you excite a molecule from the ground vibrational state and separate it altogether, that's this energy difference, V0. So we've got a couple of choices to make. First is, how are we going to define the zero of vibrational energy? And the choice that we usually make is to let the bottom of the well be the zero of vibrational energy. And that means that the energy is h nu times v plus a half. That's the vibrational energy. If we let the zero of energy be, well, there's an alternative choice, of course. You could let the lowest vibrational energy be zero. And if you did that, that would be the definition of a vibrational energy. It's really an arbitrary choice, but that's the one we use. Now, what about electronic energy? The electronic energy let's say the zero of electronic energy is normally taken as infinitely separated atoms. That's our reference. So this would actually be the zero of the electronic energy. That's the conventional choice. So the diatomic molecule electronically has a negative energy. Right? It's when you separate the atoms, that's the zero. So that has a consequence then for the electronic partition function. If you remember for the monatomic case, we saw that the electronic partition function was omega E1 plus omega E2, the degeneracy of the second level, that was the monatomic case, because in the monatomic case, the energy of the lowest electronic state was taken to be zero. Now, in the diatomic case, it's a little different. If the lowest energy is actually going to be minus dE, right? For the diatomic case, so minus dE is plus dE. So, now, very often you only really need the first term, and here's the second term in the series, and if you want super high accuracy, you can keep the third term. So, that's not of high importance, but I wanted to introduce you to the conventions for vibrational electronic energies. Any questions? So then I want to talk about the last part of the chapter, which is kind of fun to think about, actually. I think, and that's homonuclear diatomics. Turns out that there are subtle differences due to symmetry, and the expression for the rotational and the rotational partition function becomes different from what it was before. And in fact, no longer is the rotational and the nuclear partition function, no longer are they strictly separable. So that's where we're going to go. Basically what we're thinking about is if we have a homonuclear diatomic, the two nuclei, of course, are the same. And so the total wave function depends on the electrons and the nuclei, depends on the whole, everything involved. And the nuclei now have symmetry properties that we have to think about. Nuclei can be fermions or they can be bosons. Nuclei in general have spin. Some nuclei have spin 0, like carbon-12. Others have spin 1/2 or 1 or 5 halves. Different possibilities. Hydrogen has a spin of 1/2. Deuterium has a spin of 1. So depending on the nature of the nucleus, the expression for the partition function and hence for the heat capacity, for example, will be different. So how do we think about this? We really need to think about all the different contributions to the wave function, because we're thinking about the symmetry properties of the wave function. So, we often think of a wave function, the total wave function, as a product Now, we can't always factorize it this way, but let's stick with this for a second. We have to think in any case about translation, rotation, vibration, the electronic component, and the nuclear component of the wave function. What we're ultimately interested in is what happens to the wave function when we interchange two nuclei, which we're really thinking about right now. But I want to think of a slightly more complicated process. It's a better way to think about it, a two-step process. So the diatomic molecule consists of nuclei and electrons. So process one is going to be interchanging all particles. So interchanging all the electrons. Let me put it differently. There's an electronic wave function that has some symmetry properties. So what we're going to do is invert everything through the center of mass, through the origin. So all the electronic wave function is inverted through the center of origin, and also the two nuclei are swapped at the same time. Then, after we've done that, we're going to take the electrons back to where they were. So the net result is we swap the nuclei only. So first we're swapping everything, and then we swap the electrons back, leaving the nuclei swapped. So, okay, it's a two-step process. So let's think first about step one and what happens to our wave functions in step one. The translational wave function will be unaffected because it depends only on the center of mass. And when you swap all these particles, the center of mass is unchanged. Right. So there's no effect on this translational wave function by step one or step two. Right. I wanted to write down the processes so that we can refer to them. So in any case, the translational wave function is not affected by A, and it's also not affected by B. What about the rotational wave function? Well, think about no, I don't want to talk about rotation. I want to talk about vibration. Think about vibration. The vibrational energy where that's the internuclear, where R is the internuclear distance. Because of this square, the vibrational energy is unaffected by interchanging anything. So this is not affected. Now what about the electronic wave function? The behavior of the electronic wave function will depend on the symmetry properties of the electronic wave function. If you think back to quantum mechanics, term symbols describe the electronic wave function. And the general case is kind of tricky, or I guess what I mean to say is the behavior of the electronic wave function upon inversion of the electrons depends on what the symmetry properties of that electronic wave function are. We're going to get the idea simply by considering the most common ground state wave function, which is that one. And the G, which is German for even, gerade, means that when you interchange the electrons through the center of, through the origin, the wave function is unchanged. Okay. That's the most common, this is the most common ground state symmetry, so it's the only one we're going to consider. You can think about alternative cases and follow through the argument on your own. So the electronic wave function is going to be unchanged by this inversion. Okay. So what we need to think about then are the rotation in the nuclear part. Let's think first about the rotational part. Think back to quantum mechanics, the rigid rotor approximation, and remember that the problem of solving Schrödinger's equation for rotation of a rigid rotor is the same as the motion of a ball on the surface of a sphere. And the solutions to that problem have the form of the spherical harmonics. Remember? They depend, of course, on L or J. I guess I could have written a J here. We're talking J. So for J equals 0, the solution is positive everywhere. So it looks like a sphere. For J equals 1, we have various possibilities. And this means go into the board. Yeah, it looks like they're p orbitals, basically, except we're thinking of the molecule as a whole, not an electron. And for J equals 2, of course, these look like your d orbitals. But again, we're thinking about the motion of the molecule as a whole, not simply an electron. And there are various d orbitals. One of them has this little torus here, where it's negative, and there are others. Etc. And the point I want to make is that this one is symmetric with respect to interchange through the origin. This one's antisymmetric. If you interchange, you get the minus on top and the plus below. Likewise here. This one is symmetric. Yeah. So then you go on to j equals 3, j equals 4, and what you find is that if j is even, it's symmetric and odd, antisymmetric. So we have two possibilities for psi rotation, symmetric or antisymmetric. Now, what about psi nuclear? Well, psi nuclear depends. And talk about that. Well, before we talk about psi nuclear in detail, let me remind you of we use the quantum number I for nuclear spin. And just to remind you, hydrogen has nuclear spin of 1/2, of magnitude 1/2, can be up or down, plus or minus 1/2, both possibilities. Deuterium, as it turns out, is I of 1. And you have helium, you have several possibilities, depending on the isotope. Carbon, interesting case. Carbon-14, of course, is important for dating, and nuclear spin is 0. Oxygen-16, 0. But oxygen-17 is 5/2. And oxygen 18, 0. So there are various possibilities, and depending on the spin, the homonuclear diatomic will have different degeneracies of nuclear spin, and the nucleus may be a fermion, as you can say in the case of 1H, carbon-13, oxygen-17, lithium-7, these are all fermions. So then the wave function has to be antisymmetric with respect to exchange of those nuclei. Or in these cases, the nuclei are bosons, so this wave function has to be symmetric upon exchange of the nuclei. Yeah?
So 1H can be either half or negative half, correct?
I'm sorry?
You said 1H can be either half or negative half. Did you say that, or no?
Well, now let's put it this way. An individual 1H nucleus has two spin states, +1/2 and -1/2. An individual 2H nucleus has three spin states, +1, 0, -1, and so on. Okay. Depending on the orientation with respect to some experimental axis, right? And this one, 5/2, 3/2, 1/2, -1/2, -3/2, -5/2. They're all different orientations possible with respect to some experimental lab frame reference. So the degeneracy of these various nuclear spins can be fairly 2i plus 1. Now remember that our two-step process here is equivalent to a one-step process, which is just interchange of the nuclei. So the total wave function then has to be antisymmetric for the fermions and symmetric for the bosons. Depends on what you got. That's all. Now, we've seen that in step A, the rotational part of the wave function, simply from this swap, really, can behave in a symmetric or an antisymmetric way. That's the rotational stuff. What about the nuclear stuff? Well, let's think for a moment just about a 1H. It's got, of course, I equals 1/2, and we described the two possible spin functions as alpha or beta. And if you think back to basic quantum mechanics, there are 3 symmetric combinations and 1 antisymmetric combination. Right? So we have 4 possibilities in our diatomic molecule. There's our diatomic molecule. The spins can both be alpha, they can both be beta. Clearly, if you interchange the two alpha nuclei, same wave function, so it's symmetric. Now, you can have 1 alpha and 1 beta, but you can't distinguish which is alpha and which is beta. So we can't, So we form 2 linear combinations, if you recall. We can have the symmetric linear combination. So these are all symmetric. And the anti is only 1. Does this ring a bell? Does this look familiar? Maybe it's been a little while, maybe not. So we have 4 possibilities for the diatomic nuclear wave function. 3 of them are symmetric and 1's antisymmetric. So, therefore, for this molecule, a hydrogen molecule, 1H, of course, the nuclei are fermions. And since they're fermions, the whole wave function's got to be antisymmetric with respect to interchange of nuclei. Right? So we've got a couple possibilities. We can pair any one of the symmetric ones can be paired with any one of the antisymmetric rotational guys. And that didn't work so well. Okay, I just had to go more slowly. And the antisymmetric one can be paired with any of the symmetric functions. But this pairing is important. Now, interestingly, it turns out that changing the nuclear spin states is not a facile process. And consequently, it is possible to separate the antisymmetric and the symmetric. If you've got a sample of hydrogen, the antisymmetric and the symmetric or distinguish between the antisymmetric and the symmetric spin possibilities. So this case